You got the floor.
All right, let me share.
Or maybe I'll introduce you. Well, it doesn't have to be like normal paragraph because okay, so if I ran like get entry on that tree, I would get just one sentence. So the next entry would just be another thing. It doesn't have any information about what it's actually. So don't forget to share your screen.
Yeah, I'm taking it now.
Sure, you can. All right, so next we're going to cover a slightly different topic. We were focusing on spin density matrix elements in the omega, but one of the simpler measurements we could make is just looking at beam asymmetries of different particles, and Justin has shown us in the past beam asymmetries from the row, and so but for this talk we're going to demonstrate quickly just how you can do a measurement of the pi zero beam asymmetry. It'll be pretty abbreviated, of course, but it'll give you an idea how to do it.
Right. Yeah, so shifting gears a little bit, but again, it's another way of looking at polarization observables with the early data, and I'll show you a bit about why it's an easy, simpler measurement because some of the systematics cancel. Okay, so now we're changing gears on the simulation samples. We're looking at pi zero production. So this is, if you saw Janu's talk at the collaboration meeting, she was looking at this channel where you have photo production of pi zeros, and so we're looking at, it's 100,000 generated events, and here, because we're looking at this asymmetry, it's important to have both the para and the perp polarization orientations, and if you're still wondering what those are, I'm going to have a couple slides to try to explain that. So again, this is a sample that matches roughly the sample from this BGGen Sim1 background sample, and so something like 6 hours of the spring 2016 data. And we're using the full sample here, so I've made enough cuts at the JANA analysis stage that we can have the full samples in the T-trees that we're going to analyze. Okay. So Vincent is going to talk some about spin density matrix elements, but also this pi zero beam asymmetry, I think. And so I won't go into the details of the model, but it's a Reggie exchange. And so you can fit the cross sections as a function of t and make some predictions for what the beam asymmetry looks like. And we're learning something about the production mechanism in the exchange of producing these pi zeros. So this is a model I think Vincent will say something about, and we're using this model inside the GlueX software to generate these events and fit them based on the details of that model there. So there's a couple new features for this session. Since we're looking at a new channel, we need a new plugin. So this is the plugin is in this directory. Just to keep things more abbreviated, I won't go through the details of that plugin. But one thing to mention is that now we're looking at a channel where we have a pi zero as the sort of the particle that we're interested in, whereas before the pi zero was one of the decays from the omega. And so in the omega decay, we fixed or constrained the pi zero mass in the kinematic fit. But here, because we're looking at the pi zero itself in the final state, if we constrained the mass of the pi zero there, we would bias the kinematic fit and push the background into that signal. And so for when we set up the D reaction, so if you look in this directory for we have this new plugin. If you look at the D reaction code there, where you set up the reaction steps, you can set this extra flag which turns off the kinematic fit constraint for the pi0 mass. And so that's just as an example. In general, you can keep that constraint in there, and it's turned on by default. But for this example, we'll keep that off. So there's also a new deselector that we'll look at briefly, where we're applying similar histogram and cut actions as we had for the omega sample, but of course specific to this 2 gamma final state. And again, we need to remove these pi0 signal events from the background BGGen sample. So let's start. I'll give people a few minutes to go into this directory and actually execute these commands to run this new deselector for this pi0 channel. Again, we have 3 samples now: sim1, para, and perp, which are the background, and then the 2 signal samples with the 2 photon beam orientations. And so we'll go in and do that. And so I'll go do that as well while we're speaking. So this is again, the session 5B of the workshop. Yeah. There's the...
So you generated signal data with para and signal data with perp?
Yep, so there's signal generated with both the polarization configurations. And we'll talk about why that's important momentarily. All right, so once one of the samples finishes, if you run this sim1 sample first, let's see. You should have a file called hist p2 gamma sim1 accepted.root. So
could you drag that up higher?
Oh yeah, sorry, it's probably hard to see. I'll do it. So while you're running one of the other samples, you can run, for example, the para sample, and then start to take a look at this histogram file that's produced. So if we look at the sim1 sample, again, there's directories that contain the information from these histogram actions. So we have these particle combo kinematics and particle ID. So we have similar plots as before, where the most interesting one for the selection of the pi0 is this M2 gamma, so the mass of the 2 photons. And so one of the interesting things here for this channel is that, so this is the background sample from BGGen, where you've removed the pi0 yield. So these exclusive pi0 events are not in this sample. We use the same mechanism for throwing away the events from the background sample, which are the true topology. And so what you see is there's this large eta peak. And let's see, I can go to what the results look like. Once I run the perp sample. So the results of what these plots look like is something like this. So the interesting features are that for the background, we have mainly eta to 2 photons, which show up here. They have a smaller cross-section than the pi0, but they're there. You can have omega events, so these are exclusive omegas, which go to pi0 gamma, where one of the photons is lost, or it's low energy and it's not picked up, and so you get this peak near the omega mass with a tail going down underneath the eta. And then there's also some other events which there's a peaking background. So we have these cases where you produce 2 pi0s and a proton, where one of the pi0s still gives you this 2 photon mass of the pi0, and the other pi 0 is lost somewhere because it's low energy. And so this is what the yields look like for this background sample, and if you look at just the para or the perp sample, you get this very strong spike right at the pi 0 mass, because that's what we generated. So you can see that, again, with the cuts that are defined here, you can go in and look at some of the details there if you want, but with some pretty simple particle ID cuts and some the kinematic fit cut is especially powerful. Again, you can get a pretty clean sample, 4,000 events in the peak here relative to 10 or 20. So this is the sample that we'll be looking at for looking at the beam asymmetry. All right. So while you're finishing up running the processes for the 3 different samples, let's look for a minute at the polarization definition. So the polarized cross section for an asymmetry, or the polarized cross section for a process of a single meson production is really, we're going to measure this phi dependent yield, and it depends on some unpolarized cross section, and then this piece is the polarized part that depends on the photon beam polarization. So the relevant angles are the proton, and in our case the proton lab angle phi, and the photon polarization plane in the lab. And so it's really the production plane, which is the proton lab angle, and the linear polarization. The difference between those is the relevant angle. And so that's this modulation in cosine 2 phi is where you measure the polarization of the photon beam, and the sigma is the observable we're looking for. So why do we actually want to measure this in these 2 different configurations, para and perp? So we call parallel is where the photon beam linear polarization is parallel to the x-axis or parallel to the floor in the lab. So this is just a diagram of what that looks like if you're looking downstream in GlueX and you have your coordinate system here where the floor is this way. When the linear polarization vector is parallel to the floor, the angle for this photon polarization plane is 0, and so you get this phi angle is 0, and so the modulation in cosine 2 phi is really just the lab angle phi. So that's this angle for the proton pi 0 define a production plane, and it's really just the lab angle phi that gives you your modulation. So that's one angle, and so you get the relative intensity there. It really just goes like 1 minus the polarization for the para orientation times the beam asymmetry, and this cosine 2 phi is just the proton lab angle. So that gives us this modulation. So if your detector is perfectly symmetric in phi, that's all you need. You can just fit this distribution to get the phi dependent yield, and you extract out this guy. But if there was some inefficiency as a function of phi, you'd really like to have something orthogonal to that to cancel that acceptance. And so we take another orientation, which is perp. So in this case, the linear polarization is perpendicular to the x-axis. So now the polarization vector is going this way, and we've left the production plane for the proton and pi 0 in the same place. And so now we're still looking at the lab angle for the proton, but the polarization vector is now rotated by 90 degrees. And so we put in this pi over 2 factor here, and what you get is that shifts or changes this polarized distribution intensity to get a plus sign here instead of a minus. So before we had the negative sign there for the parallel, and then perp just rotates that by 90 degrees. And so the nice thing there is that if we have some inefficiency at some region in phi, the 2 effects will cancel each other because they're basically shifted by this 90-degree factor. And so when we talk about parallel and perp running in the 2 samples that we generated here, we assumed the different orientation of the photon polarization vector, and that's what we're using for the asymmetry measurement. Are there any questions about that before we go on?
How well do we know that this is 90 degrees?
That's a good question. So at the moment, I think the belief is that it's to a couple of degrees, that it's in there. But what you can do is actually include an extra phase in the way you do this fit, which can allow for some adjustment in that offset between the two angles. But we think it's pretty good. Yeah.
What runs are you looking at for this data?
This is all just simulation.
Oh.
Yeah. So we generated 100,000 events in para and 100,000 events in perp. And we're just going to look at the measuring the symmetry with that. All right. Okay, so the next step is to actually fit these phi distributions. So you can head back to your virtual machine where you should hopefully now have 3 files, which are hist p2 gamma para, hist p2 gamma perp, and hist p2 gamma sim1. And you can use the other hist or the macro that's there called hist fit asymmetry, and just execute that. And what that's doing is looking in these. So I'll open it here. That's opening these 2 files, the para and the perp file, and looking at the phi distribution. So the plots. So this is the result that you should be looking at, and I'll have a little bit more information about it here. So of course this is the simulation is basically perfect, so it's phi symmetric, and so you get for the para distribution what we saw, what we generated from what we generated is what we reconstruct. So these are the reconstructed distributions, not the generated ones now. And in perp, we get the same shifted by 90 degrees. And what we usually are looking at to measure the asymmetry sigma is this yield asymmetry. So for each bin in phi, you take the number of counts in perp, subtract the number of counts in para for that bin, divide by the sum, and put that as your asymmetry here, and do that for every bin in phi. And so the nice thing there is that if you had some acceptance gap that was happening in both perp and para at the same place, then you would cancel that in this asymmetry, and we'll see that in one of the next exercises. And then the other thing that we usually are looking at is looking at the sum of para and perp and para. And so this would show if these 2 phases are 90 degrees offset, this should be just uniform, except for any instrumental asymmetries. So if there was some inefficiency in phi, that would show up here to give a suppression. All right, so this is kind of the basics of fitting the reconstructed phi distributions to determine this beam this beam asymmetry. So what I haven't said anything about here is this beam polarization factor. We're really just measuring the cosine 2 phi fit to this amplitude that's in this macro you're looking at. Extracts 1 parameter, and you need an independent measurement of the polarization to extract this sigma.
Normally you have to normalize the 2 yields, right?
That's right. Yeah,
You
that's.
don't do that in
Well, I'll talk about that next. But for this sample, we generated the same number of events in both places, and so we're skipping that. Other questions? Okay. Yeah. So as Elton mentioned, there are experimental realities that we are not running the same number of photons are hitting the target for para and perp. And there are other things that could be coming in here, like acceptance effects or efficiencies that have a phi dependence, and those could modify the modulation in phi that we're really interested in. So these are sort of a more realistic description of what the measured yield looks like as a function of phi for the 2 different polarization states. So we have some number of incident photons on the target for each of those that are the flux. We have these factors here for the unpolarized cross-section and acceptance and efficiency. And then this is the piece that's really different between the two polarization cases. So And then finally, you have some other background, which could have some phi dependence that you need to consider. So so sort of the first thing to think about is that you have the same background in both cases, or even if it's different between perp and para, before you look at the asymmetry to try to cancel some of the systematic effects, you'd like to subtract off these background contributions. So you'd like to correct for this by, when we look at the phi distributions, if there were some background uniformly distributed here, or even with a phi dependence, you'd like to measure that independently and subtract that off of this distribution before you do the fit to the angular dependence. And so one example of that is looking at these accidentals. Jane Genu was showing this in her talk at the collaboration meeting, where most of the time we're looking at only beam photons that match the RF bunch chosen by the proton, or the pi0 in this case, in GlueX. But we do have photons which come out of time from that, and so those are accidentally tagged as the right photon for our reaction. And so what you can do is you can measure this yield for those out-of-time photons and subtract that component of the background off of the raw yield, and therefore correct for this phi dependence in the experiment. So once you've corrected for those backgrounds, then you've removed that piece, and so then you can look at this yield asymmetry. And so I rewrote that difference over the sum down here, where you can pull out some different pieces. So one thing you notice right away is that these acceptance and efficiency factors that are in principle phi dependent, if they're the same for both para and perp, then they factorize out of both the top and the bottom, and you can remove those entirely, which is really the strongest benefit of looking at these asymmetries. And then the pieces that you're left with are, as Elton was mentioning, you need this ratio of the fluxes for the perp and the para is one of the essential ingredients. And then if the polarization, for some reason, was different between perp and para, then those two factors are coming in your description. And so really something like this is closer to the functional form of the fit you would be using to extract the full asymmetry once you've either normalized the yields to account for these factors or including them in the fit. So this is sort of more of an experimental reality, and the next exercise is to go through and actually look at a case where this acceptance and efficiency are really non-uniform and see how they cancel in the extraction of the asymmetry.
Why didn't you cancel the two ratios of n perp over n parallel just for?
They only come on the first part here.
Oh yeah, I see.
So there's
I didn't see the brackets. Yeah.
Yeah.
Okay. Sure.
There's a pair right here. Okay. Other questions before we go to the next exercise?
Yes, the sum gives you a measure of the difference in polarization.
Yes. Well, it can be related to the difference in polarization or an incorrect normalization between.
Not just the height, right? So there's no phi dependence.
Well, it can be. So perp and so the n perp times p perp is what's defining so if you incorrectly normalize, then you could get an extra wave of modulation on top of the same way that a different polarization would give you an adjustment to the null asymmetry.
Factor modify the whole? Or is there an extra?
Which factor?
Sorry.
So this in para, if you just subtract these, in para goes here.
Yeah, it's
But
only the first term.
It'd probably be easier to see if the multiplied numerator and denominator by in para. Then you'd have the in paras on the right terms and the in perp.
And you would see that.
That's right, yeah. The useful piece about writing it this way is that you can recognize that you don't need an absolute measure of the photon flux, but you just need the ratio. And so that, again, cancels the systematic in the absolute normalization of the photon flux. Okay, so let's go back to the virtual machine, and now we'll add a phi-dependent detector inefficiency in the deselector. So let's go look at the deselector. So this is to simulate what would happen if, for some reason, a bracket from a air duct might hit some portion of your drift chamber, causing an inefficiency in phi, in case that might happen. So what we're doing is just for some region in phi between 20 and 80 degrees, we'll throw away 80% of the photons, or of the protons. So we're really just making some very strong angular dependent acceptance. So you can there's on the PDF file, you can rewrite that in your deselector, but this is somewhere in when you're making your loop over your combinations. We're just going to randomly reject many of the protons which are coming out in this angular range, just to remove, to cause an inefficiency in the detector.
Which file is that again?
This is in the deselector, so it's inside session 5B, this deselector P2 gamma workshop. You can look in the region where the phi angle is defined. There's a place where you calculate the kinematic variables. It's line 100 or 264 in the deselector.
I don't see it.
Yeah, you have to add it.
Okay.
Yeah. All right. Okay, so once you have that code added, you can go back and process the para and the perp runs again with this deselector, which is going to then create your new histogram files, again, that will have that this inefficiency artificially inserted in the detector. Okay. So once you have those files, you're probably still editing and adding things there, but you can run this fit asymmetry again, which will show you what the measured yields would be if you added this inefficiency. So This is just a toy example of what this might look like, but this is now, well, I guess I can switch back to the presentation. So again, we have the same 4 plots where we're looking at the yield for the parallel orientation, the yield for the perp, this yield asymmetry again, and the sum of para plus perp. So you see this place where we have this strong deficit because we just made the efficiency in the detector 20% in that region, and that's the same is true for both perp or para and perp. And so if you were to just fit those distributions without correcting for acceptance, you would get this strange modulation shifted. But what you can see, and I think we looked at the formulas earlier, would show you that even though you have smaller statistics in these bends, the asymmetry that you measure with the yield asymmetry is really canceling those acceptance effects between the 2 cases. And so that's a nice feature that if the inefficiency is the same for both para and perp, and you have this 90-degree offset, then you can determine this asymmetry even if there's some region of large inefficiency.
Yeah, it's nice to see that in practice instead of hearing about it in theory.
Well, I mean, it's in practice and simulation. But we have a nice data set that has a good hole in it that we can test it on.
Look for the good and the bad.
Right. Silver lining, we can test our theory.
You showed the code again?
What's that?
Can you show the code again?
Oh yeah, sorry. The deselector code is this guy.
It's also on your slides, right?
Yeah, it's on the slides if you're following the PDF file here.
Slide 14 on the slide.
All right. All right, so maybe I'll finish up with a few thoughts about other complications, and then if people have questions about the exercises or we want to try to fix anything that's there, we can do that. So, so as usual, life is more complicated. This is a nice picture of what this cancellation of the asymmetry or the acceptance might look like. But as we looked a few slides back, we haven't talked about the determination of these flux factors for perp and para, which have assumed that we generated the same number of events in both cases. Both the polarizations need to be determined independently for these 2 orientations as well. And so there are extra factors in here which we haven't really accounted for yet. But that's something that you really need data to look at and to look at how that works. So I mentioned earlier these accidentals that could show up that would be interesting to look at. So this is a plot of to remind you of what the time difference between the beam photons and the RF time that you select for your event. And so we have this strong peak so this is in this, if you look at the P2 gamma histograms using the plugin that was used to create these root trees, you would get a sharp spike at this delta T of 0, where this is really your prompt signal where you're selecting the true photon most of the time that produced the reaction in the target. But you do have these side bands, which are 4 nanoseconds away, which are the out-of-time photons. And so there's some peak underneath this signal, which is the accidentals, which are automatically in your sample. So our normal cut in the D reaction, where we specify which ones of these photons we want to use in our analysis, is that we select events that are within a half of the bunch period of the main peak. And so that's really just picking the things at plus or minus 2 nanoseconds most of the time. What you would like to do to actually have these candidates or these combos in your root tree to approximate what the accidentals look like is to expand that range to 1.5 times the beam bunch period. So you could set your cuts here. And so then in your root tree, you would have both the accidental out-of-time bunches as well as the in-time ones. And so you could look at these events specifically inside your root tree to see what the phi distribution is for the accidentals. And that's actually in the deselector code that you have in this session 5B. And so there's an extra plot in this root histogram which has these values in it. So you can look at these hist P2 gamma for either para or perp. And there's two histograms. One is called phi. Well, it's phi versus t, which is just the Mandelstam t variable. And then there's an accidental ACC underscore phi. And so you can make a projection of that. Let's see, I'll put this over here. So most of our signal events are really coming from these in-time photons, which are right here in this prompt peak at 0. But in the deselector, I've made a different a histogram, which is actually looking at these photons, which are out of time. And so you can see what the phi distribution looks like for the accidentals. And that's this ACC, the accidental phi distribution. And so you can make another plot of that to see what the accidentals look like. So the yield is quite a bit smaller because it really doesn't have the signal there. It's just the accidentally tagged photons. And even though we have this gap here, you can see that it does have some of this phi dependence. So some of the accidentals will look like the signal, but probably diluted by some amount. And so, as we discussed, you'd like to subtract these accidental tagged combinations from your prompt signal to really remove that effect from the asymmetry that you're observing. And Jane was talking about how we were doing this with the data at the collaboration meeting. So that's one thing to be aware of, and the place where you would go apply that selection in your D reaction is where you set up your reaction and your JANA plugin. You set the max photon RF delta T to some quantity, and you can add these accidental photons by setting it to 1.5 times the beam bunch period if you want to look at these accidental effects. The other thing that, again, I'm not going into here is that we do have some peaking background underneath our pi0 yield for our signal from this BG-gen sample. And so it's so small in this case relative to the pi0 yield, at least in simulation, that it has no effect on the extracted asymmetry. But what you'd like to do is in data use some other sideband determination of what the phi dependence is of this background. And so Sean was mentioning how you might do this in data, but you might look at things like the missing energy or the delta phi between the proton and the pi0 and look at some sideband there to be able to extract what the phi dependence is and determine a shape of the background in phi to remove that contribution to the polarized yield, which comes through in these extra background components that would be added to your distributions. So with that, I think we're at the end. Some other things you could try is actually using these accidental histograms to subtract that off from the measured yield and do the fit again, removing some of these accidental components. But I think that's sort of for the next step. So any other questions?
right.
Right.
Thank you, Justin. So, hopefully you guys know, more about how you can maybe extract some early physics results from the GlueX data, whether it's the commissioning data we've taken so far, or some of the data we'll be taking in the fall. But as you've seen, it's not as simple as it is. But in the next session, we're going to have a few talks from Adam Szczepaniak and Vincent Mathieu about how we can work with JPAC. What's the acronym exactly?
Excuse me?
Jefferson Physics Analysis. Jefferson Physics Analysis.
Joint Physics.
Joint
Physics Analysis Center.
Yeah, how we can work with them to help us understand the data that we're looking at. So that's going to start at 3:50. So we break for the next 30 minutes.